Those integration formulas on the left reminds me of the music notes on the right. What do you think? All right, now let's return to the reality. We need to continue with our discussing on section 4.3, which is about definite integrals. This is our second lecture, so lecture B, and we will talk about the notion of indefinite integrals. First, let's remind us what we learned previously in section 3.7. We say a function capital Fx is called an antiderivative of another function lowercase fx if capital F prime x is equal to little fx. All right, so basically this is a inverse process of taking derivatives. Let's look at an example. Okay, so we know that x the third is an derivative is equal to 3x squared. So if you start with a little fx, which is 3x squared, then x third is an antiderivative of our function little f. Okay. Now this is just an antiderivative because we have many other antiderivatives. In fact, if you add any constant c, it is still an antiderivative. You can show that all antiderivative will be of this way. It follows from the mean value theorem that we learned before. So if you ask what are all the antiderivatives, they will be of this form. Therefore, we say x to the third plus c are the most general antiderivatives of f. Okay, so this is what we learned before. And now here is the notion of indefinite integrals. Okay, so we write, this is just notation. So we write a notation like this. We write, hold on. Let me delete this. Okay. So we write integration of fx dx is equal to capital Fx plus c if capital Fx derivative is equal to our little fx. Okay, so this is exactly the idea of antiderivative. In other words, our capital Fx is an antiderivative of little fx. Okay, so this notation just allow us to write the most general antiderivatives of a function. So as an example, here we have 3x to the third derivative is 3x squared. Therefore, if you take indefinite integral of 3x squared, the answer is just as x to the third plus c. Now, when we learned derivatives, we learned a bunch of formulas, and each such formula can be translated to an indefinite integral formula. So here in this table here on the left, we see some derivative formulas, and I have the translation of the indefinite integral formulas on the right. So for example, we know from derivative formula that if you have fx plus gx taking the derivative, it's just equal to derivative of f plus derivative of g. And therefore, if you take antiderivative of two functions, or indefinite integrals of two functions, the result is just the indefinite integral of the first function plus indefinite integral of the second function. So I guess one comment I want to make is that this f is different from this f. In fact, the left-hand side would be better to call it capital F and a capital G. And then this derivative of capital F is our lowercase f, and then the f and the capital F will be consistent with our notion here. Okay. Likewise, if you put a minus sign here, and we know this is also correct. So in the integration formula, we also have a similar formula if you put a minus sign. And then there's also a derivative formula that says if you have a constant, you can take it outside like this. So again, if you look at the indefinite integrations, you have a similar formula. All right, and then we have the power rule for derivative, and then that can be translated to the power rule in indefinite integrations. Okay, let me explain this a little bit here. So if you just translated this directly, you're going to have something like this. Integration of this is equal to that. In other words, if you take integration of n times x to the n minus 1 dx, that should be equal to x to the n plus c. Okay, but normally people don't like to put the n here and n minus 1 here. So what they did was to first you replace this n minus 1 by n. So you're going to replace this by n, then this becomes n plus 1. Okay. Next, they divide the n plus 1 to the other side, and that's how you get the formula. Okay, if you want to explain the detail, so you're going to have something like this: n plus 1, and then x to the nth power is equal to x to the, so this becomes n plus 1, so n plus 1 plus c. Okay, so this is the n plus 1. And then you divide the n plus 1 to the other side, and then get this. Okay, and that's one comment I want to make. The other comment I want to make for this formula is that here, n cannot be equal to minus 1. What's going on here? When n equals minus 1, you get 0 on the bottom, and you cannot divide by 0. Okay, why? Well, the left-hand side becomes integration of x to the minus 1, which is, so this is my other comment. When n equals minus 1, it becomes something like 1 over x, because x to the minus 1 is 1 over x. And so you ask, what is this equal to? Okay, if you use this formula, if you're forced to use this, you're going to have x to the 0 over 0, which does not make sense. So you don't have that formula. Instead, there is another formula that you won't learn it right now. It is equal to ln x plus a constant, absolute value. But you don't need to worry about this for now. So don't worry about this until the next calculus course. For now, we simply don't allow n to be minus 1. Okay, and then we have a bunch of trig formulas. Remember, there are 6 trig functions. So we have 6 trig formulas, derivative formulas here on the left here. And each of them can be rewritten in terms of indefinite integration. So like derivative of sine is called cosine, so cosine integration is sine and plus c. Derivative of cosine is negative sine, therefore you have integration of a negative sine is equal to cosine plus cosine. But because we don't like the negative sign on the left, so we divide both sides by minus 1 to get rid of the minus sign, and therefore the formula becomes this. Okay, it's a little bit. Some people perhaps make mistakes of the sign mistakes, because when you take a derivative, sine goes to cosine. So sine, the formula for sine is still positive. Cosine formula, there is a negative sign here. But when you look at the integration formula, it's actually the opposite. Cosine formula there's no negative sign, so it's just positive sign. Sine formula becomes a negative cosine. So you need to make sure you understand that. Okay. Next, the tangent derivative is secant square, and therefore integration formula says secant square derivative is equal to tangent. Okay. And then we have a few more, 3 more. I would say those 3 are more important than the other 3. So initially try to remember those 3, but sometime later you can try to remember the other 3. I would say these 2 formulas are very easy to remember. You don't really need to work at all. You just remember it automatically. Okay. I mean the integration formulas. And then the power rule is very, very important, really important. Okay, so you must remember. So power rule you definitely need to remember. And then those 3 tricks are important as well. And then the other ones you can try to study in the coming weeks. Okay. One question you may have is that in this formulas for integration here, you have the integration of cosine, integration of sine, and suddenly you have integration of secant square x. You don't see a formula for something like a tangent, right? And because for most people, perhaps this is more important than secant square, because tangent is a basic trig function. And why is that we want to do secant square instead of tangent? That is simply because we have the formula from derivatives. It says secant square is the derivative of tangent. Therefore, we simply reverse it. And if you ask a tangent, we don't have something that whose derivative is equal to tangent. So we don't have an easy formula. This particular one can be integrated, so there is some answer, but we're not ready to do that. In general, if you have like any kind of function that you write randomly, it is generally very difficult to find indefinite integrals. In fact, the chance that you can write down the answer for a generic function, I would say the probability is 0. So we can really only do the ones for which we have the answer. So in addition to the formulas that we talk about here, there are a few additional derivative formulas that we learned that include the product rule right here, the quotient rule, and the chain rule. So can those be translated? Let's take a look. So the product rule can be translated, and it is called integration by parts. But we will not cover this in this course until calculus 2. So no need to worry about this for now. What about the quotient rule? If you look at the textbook, it's never really covered. There isn't any kind of translation of the quotient rule in our textbook. However, one can translate that, but the translation is just excessively, it's a little bit complicated, and it's not really more helpful than the product rule. So typically, we simply use the integration by parts, and that will cover any possible need related to the like the translation of the quotient rule. Okay, and then for the chain rule here, there is a translation called U substitution, and that will be covered in section 4.5. Okay. One more comment. You might wonder if there is like a product rule like this, and a quotient rule, and a chain rule. That, like for example, product rule, can you just simply take F times G and determine what the integration is? Can you take Fx over Gx and then work out the indefinite integration? Or if you take a composition of 2 functions, can you find out the indefinite integral? Well, the answer is that there isn't any kind of general formulas like this. Its integration works differently from derivatives. For derivatives, you take the product, you can just you have the product rule, so you can work this out. For integration, it's simply there isn't such a magic formula, and same for quotient and especially for the composition. So there isn't any kind of formulas like this. All right, let's look at an example. Let's say you want to compute the integration of square root of x minus 2 times the secant square x dx. Okay, so you're going to say, okay, first of all, square root of x is x to the 1/2 power. So the integration is equal to integration of x to the 1/2 minus, take the 2 out, 2 times the secant square x dx. Okay, for the first one here, x to the 1/2, you can use the x to the nth power formula. Remember, it's n plus 1, so 1/2 plus 1, which is equal to 3/2, and then 1 over n plus 1, which is the reciprocal of this, so 2/3. Okay, it's a good idea to double check whether this is the correct answer. You can do a quick power rule to take the derivative. In this case, 2/3 x to the n minus 1, so 3/2 minus 1, that is 1/2. Okay, and then times, you bring the 3/2 to the front, and that cancels with this. So this is correct. Okay, minus 2 times secant square, you just have to know that antiderivative of secant square is equal to tangent x. Okay, so that is the answer. And then, as always, you need to put a plus c at the end. All right, so this is all for the topic indefinite integrals.